with some definitions. So, section 1. So, let K be any field okay. Define the affine affine n space. So, in particular, you know, this has a vector space structure, but we will talk about much more weaker structure. So we will see that. So this has a natural vector space structure over K, but we are not interested. We are not interested in the vector space structure. We are interested in some algebraic structure, which is much weaker than vector space structure is much stronger. So this is called affine space. So now definition that algebraic subset of affine n space. So n is some integer, okay, some positive integer. So they are defined. So algebraic subsets, the algebraic subsets are defined as algebraic subsets of A and K are defined as defined by some system of equation, defined by some system equations given by, say I write this system as F. So this is nothing but the where R is in R. And what is capital R? Where capital R is a subset of K, T1, T2, Tn. R can be any subset of the polynomial ring in n variable. So the set of all solutions of F is denoted as Fr belongs. Denoted as V of F as an is an algebraic subset. So what is in simple word, it is some set of solution of some subsets of K, T1, T2, Tn. So this is a definition, or if I write it in a definition language, so if I put it as a definition language, a subset of A n K is said to be algebraic subset if it is of the form V of F, where F is a system of polynomial equations in K, T1, T2, Tn, right? K is a field. So, for example, empty set is also an algebraic set, because if you take f to be 1, the constant, then V of f is 0. V of f is empty. So, empty set is also algebraic set. And if I take f to be 0, then V of f is the entire affine space. So, empty set and algebra, the entire affine space, these are obvious examples of algebraic sets. But if I take say two systems, say F1 and F2, suppose F1 and F2 are two algebraic sets, two system of polynomials, two system of polynomials, then you can talk about their union and their intersection. So, then intersection of V of f, okay, let's write V of f1 intersection V of f2 is nothing but V of union of f1 union f2, and V of f1 union V of f2, if we talk about, this is again V of f1 f2. So, f1 f2 by definition is nothing but fi gj, where fi belongs to f1, gj belongs to, okay. So, now there is a caution that if I take a algebraic subset, what about its complement? Is it algebraic? So, the complement of algebraic subset of A in K is not algebraic, except P and A. Okay. So, some more examples. Yes, you are right. Yeah. And case. Yeah, thank you. Yeah. Okay. So, some more examples. You take, for example, suppose this is T1 axis, this is T2. Take T1 equal to T2 line. This is the example. And this is, take the axis, the union of two axes. So, this is T1, T2 equal to 0. Take the, assume K equal to R, okay. So, mostly we will talk about we will do geometry over algebraically closed field. So, in most cases they are not finite. So, yeah. So, for example, you take the parabola. These are all nice examples of the plane curves, or you take this cusp. This is equation is T2 square equal to T1 cube. So first of all, before I should have said what these are all examples of hypersurface. I mean, so here I should make a definition: the zero subset of a single polynomial f is called hypersurface. Okay. So now we need to do commutative algebra. I mean, we need to do geometry, we need to bring commutative algebra, and in commutative algebra, the basic objects are ideals. Right. This is for algebraic subsets. These are basic objects in algebraic geometry. We have to somehow relate to commutative algebra. So we have to connect to ideals. So this is the system of algebraic equations and ideals. So first of all, notice that different system of algebraic equation can give you the same set of solution. The different system of algebraic equations can give same algebraic set or algebraic subset in A and K. Yeah. So sometimes I will not write it. Algebraic subset means they are subsets in some A and K. So I will not write algebraic subset. So for example, if suppose f is a system of equation. So f is a subset here in K, T1, T2, Tn. And if I adjoin something like f union G, call it f prime, where G you can write it as summation fj gj, say j equal to 1 to k, and fj's are in f, then you will see that v of f prime and v of f they are same. Okay. So this is so you just this you check. Okay, I will not write. So now in general, so you make a equivalence class among all system of equation. So in general, we say that two family of equations f and f prime are equivalent if v of f is equal to v of f prime, if their solution sets are same, right. So for example, if or this is equivalent of saying that that any member of f can be expressed in terms of linear combination. So, linear combination means okay, in terms of, so let us not, with coefficient in the kx1, kt1, t2, tn in terms of f prime and vice versa. That means, if I take any polynomial in any element in f I can write it as summation fj prime gj prime, where fj prime is in f prime. Similarly, any element in f prime I can write it as summation fj gj. Okay. So, these are but the problem is that this is not a good thing, because for example, f and f power r, v of f and v of f power r, they are same, but they are not equivalent, right. So, because f you cannot write it as some g times f power r, some polynomial, because f is a lower degree. So, there is some issue. So, I should so maybe it is not so one implies another, so it is not exactly equivalent. So, we want something like this. So, so in general, so let us write, say two family are equivalent if exactly it is not equivalent, but it is close to that. Okay. For example, you take f x y and f prime x plus y, x minus y. These two are equivalent. Where any member of f prime, you can write it as linear as member of f, or similarly if you can write it. So, these are two equivalent, f and f prime are equivalent. So, this is so what I said just now, this is a note of caution, that equivalent algebraic system so when I say algebraic system, means algebraic system of equations have identical sets of solutions however sorry, two non-equivalent system may give rise to same set of solutions. Okay. So, there something needs to be done. Okay. So now you define a weak equivalent. You define in view of these two. So, the new definition. So, two family f and f prime to be weakly equivalent if every element of f has a power F for R that can be expressed algebraically in terms of F prime. So, in some sense what does it say that you take the, I mean, since you know commutative algebra, the ideal generated by F and ideal generated by F. So, any element in the ideal generated by F, it is in the radical of the ideal generated by F. So, we will come to that. That is the Hilbert-Nullstellensatz. We are going towards that. So this is, so now weakly, so first, so with this a weakly equivalent system of algebraic equations have identical set of solutions. So this is the motivation to do Hilbert-Nullstellensatz. So I define ideal of a algebraic subset for any. See, when we define algebraic subset, we defined as a 0 set of some system of equation. That system of equation need not be an ideal or anything, it was just a subset, right. But now to do commutative algebra, you need to bring ideal. So now you start with any algebraic subset. I want to go to a ideal. So for any algebraic subset, V in some affine space define the ideal of definition, ideal of the variety or ideal of the algebraic subset as all those f in K T1, T2, Tn such that f of V equal to 0 for all V in V. And now you check that IV is an ideal. And it is called the ideal defining the variety V or the algebraic the algebraic set, the algebraic. I have not said what is a variety so far, defining the algebraic subset. Okay. So now you notice that if you suppose you take so instead of the subset, you could have taken an ideal. Ideal is also a subset. So for example, suppose the ideal I is the unit ideal. Then so if you take the system of equation as I, then V, what is V of I? V of I is phi, right. But what about what about the converse? Suppose V of I equal to phi, does it imply that I equal to I is unit ideal? This is I this implies. What about the converse? Suppose V of I is empty, can you say that I is the unit ideal? So you need to assume something. So suppose K is algebraically closed. We need something. Assume K is algebraically closed now onwards. Okay. So this is an important assumption. We need it. If we assume K is algebraically closed, then the converse question answer is yes, if this is also true. So, this is a if and only if condition, that if you take a ideal in k x1 x2 xn and if the 0 set is empty, if and only if I is a unit ideal. So this is the answer. This converse is called weak Nullstellensatz.